So we're going to be starting talking about what is blockchain, and just take a brief look at the tech. If you are already familiar with blockchain, don't worry, we're only going to have a couple of slides on this. But I just wanted to make sure that everyone here is kind of on the same page when I talk about blockchain and what this can actually do as a technology. So at a fundamental level, a blockchain is just an instance of what is commonly called a distributed ledger technology. And for blockchain specifically, there are kind of three key things that every blockchain enables for that ledger. So when we say distributed ledger, we're just talking about it's basically just a database that's distributed on many computers. And the key thing here is that this is a decentralized network. So we have a bunch of nodes in a network running this software, and they all come to a consensus about what the state of the ledger is. So this isn't a case where we're relying on one centralized server to provide all my data, and we don't just have a bunch of different instances of similar software but saying different things. The key is that it's decentralized but still a single source of truth. And an important part of that is the fact that it's also trustless. So by being trustless, I mean that the data is always accessible and verifiable. I can tell someone that I sent them $5, but how do they verify that I actually did that? And we can do that not with just asset transfers, but any sort of data that happens on the blockchain, and we'll talk more about the different kinds of data that can exist, that can be independently verified by anyone. So maybe you're talking to a node in the network, and it tells you something about the current state. You yourself can run your own node and verify that everything it's telling you is indeed correct. And then finally, a really important piece of blockchain is being immutable. So once something happens in the ledger, then it can never be undone. And this is really important for kind of what we just talked about of data being accessible and verifiable. I have full access to the history of the chain, therefore I can always make sure that what the current state that someone or something is telling me is true, and I can do that by looking through the immutable history and making sure the state is as I expect it to be. So how do we do this? And we do this through a chain of blocks, hence the name blockchain. So kind of taking a step back, we work in fundamental units of blockchain is really transactions. And these are just database transactions, right? So a database transaction is just some unit of work that changes the state of the database. And so a transaction, we use that to identify state changes in the ledger. In the case of simple blockchains, this is just like I lost some money and someone else gained some money when I did a transfer. As we'll talk about, there are more types of state changes and more types of applications for blockchain, but the transaction is kind of the unit that describes how we're changing the overall state. Now with blockchains, we have a network of nodes and they need to come to a consensus. And so it would kind of be inefficient if every single transaction was independently verified every single time someone transacted. So what we do is we group transactions together in what we call blocks. And these blocks are just an atomic collection of transactions. So when I transfer someone some money, that's a transaction, and then a block contains multiple transfers. And the network agrees on those blocks together rather than verifying each transaction separately. And then finally, the most important part is the chaining. And we do this by using cryptographic hashes. And we essentially link the previous block of transactions to the next block of transactions. So whenever I'm replaying the history and I want to verify that the state is what I expect it to be, I can use these cryptographic hashes, which are one-way functions, to verify that the history hasn't changed. Because if someone were to change anything in that block, its hash would change, and that would affect all the subsequent hashes. So by having these blocks of transactions all being hashed together, they're chained together in an immutable way, backed by these one-way cryptographic functions. So the key here is not just that we have a bunch of nodes running software, right? It's the fact that they're all agreeing on what the state of that software is, right? What the state of that ledger, the state of the blockchain. And so the key with blockchains is that we have a trustless model. anyone can participate in the network. So if I want to participate in some blockchain network, I can run a node, a Raspberry Pi, phone, depending on the network, it could be anything, and start participating in the network and say that I want to add information to the network, right? You can imagine if we have just like a piece of paper with a ledger, who has the ability to write on that and who ultimately dictates what the state is, right? You can imagine if I could just join the network and say I have $1 million now, that's obviously a problem. So we need a way to figure out who has the rights to add to this distributed ledger. And this was really kind of the fundamental problem with blockchain that it solves, right? So not only is it just about decentralization, but it's about disintermediation and removing the necessity to trust the counterparty or any individual in the network. So there are kind of two main ways that this is done in various blockchain networks. The first of which is proof of work. And this basically says in order to add to the chain, you have to solve a compute-intensive hashing challenge. So this is what most people, when they think of blockchain, they think of Bitcoin and mining and really expensive GPU operations. That's what proof of work is. It's using, in most cases, like a GPU or an ASIC, which is just like a specialized computer for mining, and running a bunch of hashes over and over again until it finds a hash that matches the pattern that the network expects. And so this is a great way to ensure that kind of the logic is that anyone that is spending that much resources into adding to the network, they're disincentivized from trying to act maliciously. Because if they kept trying to act maliciously, then it would cost them a bunch of compute resources. Now, the alternative is, and this is what we're starting to see on more modern blockchains, is proof of stake. And proof of stake means in order to add to the network and change what the state of the ledger is, I need to hold a stake in the ledger. And this is a much less technical approach and a much more game theoretical approach, with the basic idea being that I'm not going to make changes to the ledger that negatively impact the ledger if I value the data that's on the ledger, right? So in the case of a blockchain, if you hold stake, that means you hold a lot of the native token that has some value. And if you were to do things that negatively affect the network, you're implicitly negatively affecting the value that you hold on that network. And so that's kind of the base idea with proof of stake. And really the key, again, is, with both of these, is that we are just solving the problem of who do we trust, right? We want to remove that element of having to trust someone to write to the network. And that's what proof of work and proof of stake solve. So that's a quick briefer on blockchain technology, but you are probably want to know, okay, that's great, but what can it actually do? And so that's what we're going to be focused on before we get to the code, is just talk about some use cases that use Algorand to build real-world solutions. So I want to first start off with this company called AgriToken. And AgriToken is a company that digitizes agricultural goods. So this is a very common use case for blockchain. We have some asset in the real world, and we want to represent that in a digital fashion. And with blockchain, we're able to represent various real-world assets on-chain, inheriting the decentralized, immutable, trustless properties of blockchain. So in this case of AgriToken, they work with farmers, particularly in Latin America, like Argentina, and they allow farmers to tokenize or digitize their crops. And this is really important because it provides usable liquidities to those farmers. Typically, if you're a farmer, you don't get the money until you have grown the crop and you've sold it to someone. But what we want to happen is we want a farmer to be able to represent their crops somehow and be able to use that representation in the real world. So they represent their crops, like an example is soy. There's a digital representation of soy on the Algorand network, and then they can go to a bank and get a loan, or they can go to a store and use a Visa card. And at the tap or during the time of the loan, they aren't transacting in fiat currency. They're transacting in soy, but they're transacting with a digital representation of soy. And of course, they can also use this with other farmers to purchase supplies as well. And so the key here is that we're using blockchain as an infrastructure, as the rails for this sort of payment, right? Because the fundamental solution is they wanted to create a new currency that, instead of being backed by their government, was backed by the crops that they grew, right? And so blockchain was the piece of infrastructure to do that. But like any other product, there isn't just one piece of infrastructure that makes or breaks the product. There are various pieces of infrastructure that all interact with each other. So, for example, an AgroToken, yes, they use blockchain to digitize the assets, to digitize the soy. But they also work with reliable institutions, like banks and exchanges, to ensure that there's pricing fairness and to make it more interoperable with these companies like Santander and Visa to provide loans and actual payments. So the key with blockchain is that it's really just another piece of infrastructure that offers you the benefits of decentralization and immutability and disintermediation, but it's just a piece of the product that you're building, right? It's unfair to say that using blockchain is the only piece of technology you use, right? That's not true for any piece of infrastructure. So the key here, and as demonstrated by AgroToken, they're using blockchain in order to interact with the real world in a disintermediated way. And so this is a great example of tokenization, which is a very popular use case for blockchain, which is just what we call it when we represent digital assets or physical assets in a digital way. Now, another common use case for blockchain is using it as financial technology, right? Just very simple payments platform. So this is a solution called Hisab Pay, and this is a interoperable digital payments platform. And particularly, it's a platform that's used in Afghanistan. And you could basically think of this like a Venmo or a Cash App or an Apple Pay, and it's used kind of just day to day, right? The citizens use it for bill payments, in-store purchases, peer-to-peer transfers, just regular day-to-day stuff. But in the back, Hisab Pay is using Algorand to power those transfers that are happening. And this is a great example of blockchain usage because it's not just about the fact that we're using blockchain in that we have all these decentralized, immutable, like all those properties. That's great, and it's really important in areas like Afghanistan where there are a lot of people that don't already have fair access to financial instruments. However, another really great thing about blockchain that's kind of just implicit is the fact that it's a open source, standardized specification for issuing financial instruments, right? So, for example, Hisab Pay, they're an independent company. Like I said, they operate in Afghanistan, but they also work with the UN World Food Program to disperse funds. So the UN, they go to companies like Hisab Pay and integrate with them in order to disperse the funds for aid. And for those that aren't familiar, the World Food Program, basically their mission is to address hunger and citizens in need. And they do that by dispersing funds. And in this case, they do it through Hisab Pay. And the value here is that as we work more with Hisab Pay in the World Food Program, we can see how we can scale this to other areas in need and for Hisab Pay to work with other companies, right? Because at the end of the day, they're just using the blockchain technology, right? They're using Algorand. So there's a known set of standards. There's a known way to read that data, a known way to write that data. And so if the UN wants to work with another platform in another country, they already know how to use the underlying payment rails, which is Algorand. So it makes that easier for them to scale, like horizontally scale, how easily they can work with other humanitarian organizations and disperse those funds. So I think this is a good example of kind of one of the implicit benefits of just open source software in general and open standards, and that various companies can leverage repeatable processes by using these standardized interfaces. Now, another example, and this is another example of tokenization, is TravelX. And in particular, this is focused on ticketing. And what TravelX does is they help airline companies tokenize, which is turning airline tickets into non-fungible tokens. So I'm sure you've all heard of NFTs, and you probably associate them with like memes and dogs and stuff, which is great, but there's also real-world solutions that are leveraging NFTs to solve actual problems. And in the case of TravelX, kind of the main reason why an airline might want to use TravelX and thus use Algorand is the headline feature is the peer-to-peer ticket marketplace. And so this is by using blockchain, right? Again, it's an interoperable standard. It's decentralized, immutable, but it also allows disintermediation, right? So now an airline that uses TravelX, they don't need all the customer service costs that are involved for being able to provide refunds. They can also have noticed an increase in early purchases, right? So because we have this peer-to-peer and disintermediation, we've lowered costs and increased revenue by making the customer experience easier, right? If I buy a plane ticket, I'm not sure if I want to use it or not, it's very easy for me to find a buyer in the peer-to-peer marketplace, and the airline itself doesn't need to get involved at all. And TravelX is another great example of using blockchain as infrastructure, but not using it as just like a marketing thing, right? Most people, so TravelX has millions of users because they've partnered with domestic airlines in Latin America, and they have millions of users already, but none of them really know they're using blockchain, right? So again, I just want to drive home the fact that this is infrastructure that is being used by a company in order to reach the goals that they want and provide the solutions they want, even if the end users might not necessarily be aware that they're using blockchain. Now, another great example is Lofty, again, representing real-world assets on-chain. And this is an example of fractionalized real estate. And Lofty is a really good example of taking an existing solution and using blockchain to increment, random Discord update. Okay. And we can use Lofty as an example to kind of show how we can take an existing solution and then increment on top of it. So real estate, kind of the general problem is that in order to invest in real estate, you need a lot of capital, especially if you want a diverse portfolio. And we've seen some like solutions in traditional finance, like real estate investment trusts. But those investment trusts, I mean, they require trust, and they also require like a lot of administrative fees for those managing the trust. The people that are in the trust might not necessarily have control of how those properties are managed. And so Lofty uses blockchain to further improve that fractionalization of real estate and make it easier to get exposure to real estate and have more diverse real estate portfolio. So with Lofty, you can invest in real estate properties, most of which are residential, but there's also some commercial as well, with just $50. So if I want exposure to the real estate market, I can just invest $50 and I get that exposure. But the key with Lofty isn't just that I'm getting some return on investment, but I'm now actually a owner and manager of that property. So with Lofty, when you buy one or more tokens, you actually become an owner of that property through an LLC. And the ownership is tied to the ownership of those tokens. So on average, each listing on Lofty has 231 buyers per home. So that means whenever there's a decision to be made, like what property management company should we use to manage this property? What fixes should we do? How should we deal with eviction? Right? All these things that involve that are required to manage a property are decentralized and just dictated by who owns the tokens. Now, finally, we have an example of DeFi, decentralized finance. And in this particular example, we have Folks Finance, and this is a DeFi protocol on Algorand. And decentralized finance is basically about providing some existing, some new financial tools using blockchain technology. So, for example, on Folks Finance, we have common financial instruments that everyone's used to, loans with like lending and borrowing, right? It's same concept, except we've now decentralized, disintermediated. So I can now take a loan without having to trust the counterparty. But blockchain also enables some new use cases that haven't yet been possible. So a really interesting example of that is called flash loans. And this allows people to access liquidity and access capital to make trades that they didn't previously have. So an example of a flash loan is because on blockchain, we can have those atomic blocks of transactions, and I can programmatically guarantee whether something is going to happen atomically, so happen together or not. That means I can borrow 100,000 US dollars, make a trade with it, Discord again, make a trade with it, and then pay back that loan instantly. So even if I had $0 to my name, I could make a trade with $100,000, and either it works and all the logic checks out, and I just pay back, some fee on that loan, or it doesn't work and nothing happens and I don't lose any money. All right? And then another example is swaps, and this again, it's all about disintermediation. I have some asset, you have some other asset. Let's trade. However, you're not going to get my asset if I don't get yours. So it's kind of like an escrow without that escrow account in the middle. So it's an atomic swap happening trustlessly. And again, with DeFi, kind of the main thing is that it's non-custodial. So you're not trusting some bank to manage your funds, or you're not trusting, FDIC insurance. You just are the one that is managing your funds digitally on the blockchain. And the nice thing here is that, again, we can be interoperable with the real world, because as we've seen, we've been able to tokenize real world assets, and then we can further use those assets in these new financial instruments. So example is Folks Finance. They support doing all these DeFi primitives, so things like lending, borrowing, flash loans, with digital representations of gold and silver. So by combining tokenization, right, digitizing these existing assets and these DeFi primitives, you can do things with existing assets that haven't yet been possible before. So the goals of those slides were kind of not just to picture those projects, I think they're cool projects, but kind of to showcase that blockchain is usable as a real piece of infrastructure for real solutions and products that can find product market fit. So now the question is, we can see that, and we can see that there are products that can be leveraging blockchain as infrastructure. But now the question is, why should we choose Algorand, right? A lot of those projects, if you were to just kind of believe the face value of what every blockchain can do, you might think that you can use any blockchain. But as with any technical piece of infrastructure, there are a lot of technical details and trade-offs with each different solution. So to quickly give some context, there's been a couple of blockchain generations, and this kind of outlines the way blockchain has evolved. The lines are kind of blurry in terms of where you want to draw the line between generations. And it's not always necessarily the case that one generation is significantly better or 100% better than the last, but this has kind of been the overall trend in evolution of the technology. So the first generation is Bitcoin, and this was a focus on digital currency, right? So representing value digitally, how do I do that? And really the key innovation with Bitcoin was solving a double spending, right? So the idea of having a decentralized network that can be used to transfer value wasn't necessarily new with Bitcoin, but what it figured out is how to properly stop malicious actors from spending assets multiple times, right? In any digital context, preventing duplicates is a very challenging problem. And so that's really how Bitcoin kind of led this blockchain path on blockchain innovation by solving double spending. But then the second generation came with Ethereum. And this was when the concept of smart contracts were introduced. And so what smart contracts are is they're a way for users of the blockchain to define the logic that nodes in the network use. So on Bitcoin, for example, the only logic that's happening on each node in the network is, does this person actually have this Bitcoin to transfer to this other person? Right? It's very simple logic. But what smart contracts allow you to do is attach custom logic to those transactions. So that's what allows us to do these more complex features like flash loans, for example, or peer-to-peer marketplaces. We can use smart contracts to dictate when transfers can and can't happen and to modify the state of the ledger. So that was introduced with Ethereum, and that was a pretty big change and allows for a lot of the exciting things that we see on blockchain today. But the main problem is that they are very slow. So Ethereum and other similar chains are slow and expensive. And as a developer, you don't want to be paying a ton of money for slow infrastructure. And so that's where the kind of the third generation, and Algorand is an example of that, of blockchain comes in. And the real focus there is scalability, right? So we have these cool concepts like digital currency and no more double spending and smart contracts. But how do we actually turn that into a usable piece of infrastructure that we can reasonably use to solve actual problems? Now, you might be wondering, why didn't Bitcoin just do all that from the beginning? And it's because there is a blockchain trilemma that a lot of people like to talk about. And this kind of highlights the key features of a blockchain that are hard to balance. So every blockchain should be decentralized, secure, and scalable. But often you kind of have to make compromises when you want one or the other. So for example, if I want something that is super fast, I just make it so that every node in the network is a supercomputer. But not everyone has a supercomputer, and there aren't a lot of supercomputers in the world, so the network is going to be more centralized because not that many computers can actually do the compute that is required. And so the idea here is that we want to balance all these things, and we want to find a good balance where we can be decentralized, so we're not trusting one entity to control the network. We can be secure, so people can't just join the network and start breaking the rules and printing money out of thin air and all that bad stuff that can happen. But we also want to be scalable, right? We want to be applicable as actual infrastructure that people can use, right? If we're too slow, then it's going to lead to a bad UX, and people aren't actually going to want to use that infrastructure. And so with scalability, kind of the main two things is, what is the throughput of the network, right? So right now, how many payments can it handle in a given second? Or another kind of approach is the horizontal scaling. And that question is, as the network gets bigger and bigger, how does that affect the dynamics of the network, right? So for example, let's say I have a blockchain that just stores the entire ledger in memory. That's going to be super fast, but as more people start using that ledger, it's going to get bigger and bigger, and I'm going to end up needing terabytes of memory, right? Which is not good, because nobody has terabytes of memory just lying around, and it's going to be more and more centralized as it gets bigger and bigger. So the idea is to find the balance between all these three things, and every blockchain, including Algorand, is working on improving these every day, but the key is finding that good balance point. And so the assertion with Algorand is that we've solved the trilemma, right? So again, like I said, these things, there's always room for improvement in every piece of infrastructure, but we think we've kind of hit a really strong balance of these three aspects, and that is what enables Algorand to be such a compelling piece of infrastructure. So kind of an overview of the brief anatomy of Algorand, and each of these bullet points could be a whole presentation on its own. But kind of the high level is at the heart of the network is the pure proof-of-stake consensus mechanism, right? So every blockchain, the key thing is, how do all these nodes agree to what the current state is? And on Algorand, we have what's called the pure proof-of-stake consensus mechanism. And this is what is used by all the different nodes in the network to agree on that ledger state and agree when someone tries to write to the ledger, is that actually valid or not? And the way we do that is we use proof-of-stake, and we use a cryptographic primitive called VRFs, or verifiable random functions. So for those of you that have worked with randomness, you know randomness is not easy to do. And in the context of a decentralized network, we also need a way to have verifiable randomness, right? So in the case of a proof of stake network, basically how it works on Algorand is that it's like a lottery for choosing who can actually add to the ledger, who can participate in deciding the validity of things that people are trying to add to the ledger. So there are multiple steps that people get involved. But the key is that lottery is dictated by these verifiable random functions. And that allows people to essentially generate their own lottery tickets and tell the rest of the network, hey, I have the winning ticket. But the rest of the network needs a way to verify that it is indeed randomly generated through a known function, and that's what VRFs do. Now, in the pure proof of stake consensus mechanism, that's what is kind of the low-level details. How do we agree on what's right and what's wrong? But kind of the blood of the network, what's actually happening day to day on the network are these transactions. So these can be payments, asset transfers, app calls to these smart contracts, et cetera. And then the brain of the network is the Algorand virtual machine. And this is the environment in which smart contracts are executed. So in most contexts, right, when we're writing a program, we're expecting that to run on like x86, instruction set. What we do with blockchains is we basically write a software virtual machine that has a limited instruction set. Because we have a bunch of nodes in the network and we want those nodes to be relatively easy to run, we don't want to make it so you can do anything you want in a smart contract. We want to have a limited set of instructions that are very optimized for blockchain use cases. And the Algorand virtual machine, it can perform many different operations, ranging from like simple addition, adding two numbers, or advanced cryptography, like verifying points on an elliptic curve. Now, when we talk about blockchain, there are a couple key metrics that you as a developer want to be aware of. All right, so the first one is block time. This is pretty straightforward. It's the time it takes to add a block to the network, right? So I tell the network, hey, I want to add this block of transactions. How quickly does the network say, okay, that block has been added? Then we also have this idea of finality, and this is the time to guarantee that a block won't get reversed. And this might sound kind of counterintuitive because we've been talking about immutability, but there are some networks where blocks can end up getting reversed, and we'll talk about that in just a second. And then finally, we measure the transactions per second, and this is basically the bandwidth of the network, right? How many things per second can this network do? And for Algorand, we can do about 10,000 transactions per second. We have 2.8 second block time, and we have instant finality. And this basically means, as a user, if I want to do something to the ledger, so if I want to transact with someone, if I want to interact with a smart contract, I send the transaction, and about 2.8 seconds later, I get a confirmation that the transaction was added to the network, and I can be assured that that block that contains my transaction is not going anywhere. And that transaction, for the next however many years, decades, centuries, the Algorand network is running, is always going to exist in that block. Now, you'll notice that I used big, bold, highlight, and italics on instant finality. And that's because it's very important. And if you're not familiar with blockchain, you probably think that that's the way that all blockchains should work, right? We're talking about immutable infrastructure. How can immutable infrastructure get reverted? And so, again, much like earlier when we talked about the trilemma, it's not as simple as, Bitcoin should have just done that from the beginning. The reason why that's not a given for any blockchain network is because of the cap theorem. And the cap theorem basically states that for any ledger technology, blockchain or otherwise, this also includes for like MongoDB, MySQL, like any ledger technology used as infrastructure, you basically have to pick two of these three things. The first of which is consistency, which in the context of a blockchain, do all nodes have the same state? Then there's availability, which is the network accepting new transactions? And then we have partition tolerance, which is about can the network continue after we have disconnections and disagreements? Now, every blockchain needs to have partition tolerance, right? Because if It's decentralized, it's permissionless, anyone can join the network. So if one node goes down, we want the network to be able to continue running. So partition tolerance is basically required. And so now the question is, do we choose availability or consistency? And a lot of blockchain networks choose availability, which means the network is able to add blocks, but the data won't be consistent. So it's possible for those blocks to get reverted. On Algorand, we've made the inverse decision. We've chosen safety over liveness. So our network is partition tolerant. We have a specific recovery mode in case too much of the network goes offline. But importantly, we're consistent. Our blocks can never be reverted. Once you have confirmation that the block has been added to the chain, it's never going to be reverted. On other blockchains, it's possible that you may think your block was added to the network, but it then ends up getting reverted. This means, however, that while we're in recovery mode, that we can't add any new blocks. So the decision here was we thought it was preferable to ensure that all the data written to the chain was always correct, rather than sometimes allowing essentially incorrect writes. Now, let's get to what we're all here about, Python. So on Algorand, you can build smart contracts, front-end, back-end code, all using Python. So same language, we all know, but we can now leverage new blockchain infrastructure. And this is kind of a high-level overview of what Algorand Python tooling looks like. So kind of our premier entry point into the Algorand developer experience is this package called AlgoKit. And it's a CLI tool for project creation, environment setup, actual development, code generation, and deployment, right? So you don't have to manually fiddle with VMs and make sure you got all your dependencies set up. You can just use AlgoKit to do all that for you. And we also have AlgoKit utils, which is basically our library for interacting with the chain. So this is code executed off-chain that wants to read or write data to and from the chain. And then finally, we have, I just noticed my term, sorry about that. Finally, we have Algorand Python, and this is kind of the headline feature that we're really excited to share today. And this is a Python AST compiler for the Algorand virtual machine. So with Algorand Python, you can write smart contract code that is fully native Python, but instead of running in the Python interpreter, it runs on-chain in the Algorand virtual machine. So what does this mean? This means you can write your full app, including the smart contract, in any Python-compatible IDE, because again, it's just valid Python. It's compatible with any linters or formatters, any tooling that works with Python source code. And we also leverage static typing for compilation efficiency. And this is important to mention because, like I said, we're not running in the Python interpreter. We're using the Python language to target the AVM. And so we have some slight differences when we develop on Algorand, like we have to use static typing. But because we're using static typing, all of the code that we write is fully syntactically compatible with Python. So this means this code is intended to run in the Algorand virtual machine, but we can also write like shim layers for testing to execute that code in the Python interpreter as well. So that was a quick overview at the kind of concepts that we have when it comes to Algorand and blockchain. So now we actually want to get to the exciting part and take a little look at what it looks like to build on Algorand. And so what I'm going to be doing is I'm going to be stepping through the smart contract code and then the test code that we used to test that using Pytest and show what that looks like. Before I get into the actual lines of code, I want to briefly show that if we take a look at our project here, you can see we have a directory structure with in here we have our smart contracts, and then we also have a directory for our front end that's using React. And this entire project directory structure was instantiated by the AlgoKit CLI. So the AlgoKit CLI has a command called AlgoKit init, and I run that, and that'll give me this structure for me. So again, it kind of solves all of the setting up your VMs, setting up all your dependencies. By running algokit init, we get this project, and we just have to come into our smart contracts directory, go to our contract py, and we can start writing Python code that executes on chain. So what I'm going to do here is kind of walk through the code for this digital marketplace contract. So this contract is the code that allows someone to list an asset for sale, and then any counterparty to come and buy that asset for the listed price. You can see here our module called AlgoPy, and we import a bunch of different utilities that we're going to use to interact with the chain. I'm not going to go over each one here because we'll get to it in the code, but kind of the base idea is that because we're executing in the Algorand virtual machine, we need these new classes to interact with the native primitive types in the AVM, and so that's where all these imports are going to be doing. But taking a look at the actual definition of our logic, right? So how do we define what the logic is? We just instantiate a Python class. In this case, it's called Digital Marketplace. And we're going to inherit from arc4.arc4 contract. And arc4 is the standard. So arc stands for Algorand request for comment. That's the standard for defining the application binary interface. So ultimately, the AVM just works with ones and zeros like any other computer. So we need a way to tell the AVM, or to tell the compiler in this case, how we convert our Python code to those ones and zeros. And so that's what we get when we inherit from arc4 contract. It takes care of all of those ones and zeros for us, so we can just write regular Python code. Now, once we start getting ready to write our actual logic, the first thing we do, like any other class, is we define the state in that contract, right? The state in that class. In this case, we do that by defining properties. So again, this is going to be a digital marketplace. I want to be able to list an asset. I need a way to tell anyone that wants to interact with this contract what the asset I'm listing is. And in this case, every asset on Algorand is identified by a unique 64-bit unsigned integer. Then what we also want to do is we want to list a price. We don't just want anyone to be able to take that asset. We want to be able to say, only give this asset to some buyer if they give me enough. So by defining these two properties, so all we've done here is we have these two lines of code that defines values that is going to be saved in the ledger across the thousands of nodes in the Algorand network. So just by defining these class properties, we've defined the state that this contract is going to contain in the ledger. So you can think of the ledger itself as a big state machine, and this smart contract as a smaller state machine, and this is the state that we're going to be working with. Now, to actually make our logic callable, we need to define some methods. So again, we're going to be using this arc4 utility. Part of arc4, part of the application binary interface is how do I call a method? So we're going to say it's an API method. And then we just define some context about this call, right? So when I call this app, what do I want to be allowed to happen? In this case, this is going to be a no-op. In other words, not do anything special. Later on, we can change this to a delete. So we're going to find a method that deletes our application. And then because we're going to be defining a method called createApplication, that is going to be what deploys our application on the network, we're going to require it to be called when we create the application. Now, if we take a look at the method itself, this looks like any old Python function. We have an argument, that's the asset we want to sell, the price that we want to sell that asset for, and then we just update the state. And again, this is just 2 lines of code, but what we've done with these 2 lines of code is on thousands of computers in the network, we've saved this information, and because this was a createApplication, we've now deployed our entire program on those thousands of computers in the network. And so now, I want to define the other methods that are going to be useful for the owner, right? So I want to have a method to set the price. So if I list an asset and I want to change the price, I'm going to define a function set price. I pass in a unitary price, so how much per unit is the person paying? And then we go into our logic. And this is a very common pattern in smart contracts, is asserting something about the transaction itself. So in this case, I don't want to list an asset and then anyone can change the price, right? Otherwise, someone's going to change the price to 0 and they're just going to steal everything. So what we want to happen is we want to do an assertion. I want to assert the person sending this transaction is indeed the person that created this app. So we're going to see, are you the person that listed this token for sale? If so, you can change the price. And then once we've done that assertion, we can go ahead and update our state. And now looking further, this is a good example of how the Algorand network works with atomic transactions. So in order to transact with an asset on the Algorand network, we need to what we call opt-in. And this is basically telling the ledger that I want to pay for the space that this asset's going to take in my account. So every account, or actually taking a step back, the Algorand, every node is running an SQL-like database. And so every time we want to do something that increases the size of the database, we need to pay for it. And so what we basically want to happen is we want this contract to pay for the space that holding that asset is going to take. And so now, what I do is I define a method to opt the contract into the asset, and then I require an atomic payment. So the user is going to call opt into asset, which is going to be a call to this logic. But that logic is going to require an additional atomic payment transaction. So if someone tries to send that payment, or someone tries to call this method without the payment transaction, it'll fail. Again, this is leveraging the atomicity of blockchains, and particularly of Algorand. So we can guarantee that certain things happen together, and if those things don't happen together, then the transaction group will fail. And in this case, we're verifying that the contract needs to pay for this asset, and so we're verifying the user calling it is thus paying the contract. Right? So here, I'm not going to go too in-depth in here, but here we're just doing some asserts on our state. Again, this is just a state machine. We want to make sure that our state is what we expect. So we make sure we haven't already called this method, and we make sure that that other transaction, that payment, is going to us, and that it's the amount we expect it to be. And then in our contract, we can then send a transaction. So in the contract, we can require our end users to provide a transaction, but we can also execute a transaction of ourselves. In this case, this is a transaction to opt into that asset. Now coming down, this is another method that end users are going to be using. So this is a buy method where we pass in the atomic transaction to pay for the asset, and we specify how much we want. So if I want to buy an asset, I call this buy method, and I group it together with the payment that pays for the asset. So I can see here that I'm just doing, again, state assertions, making sure my inputs are what they expect. And then once I've verified that that payment is valid, so I've verified that the payment is getting sent to me and that it's actually the amount that it needs to be, I can then go ahead and transfer that asset. So again, we have this logic that is making sure all these various steps, right? So we have the call to the app, we have the transfer to the app, we have the payment to the app, and then we have the transfer of the asset. And we're able to do that all atomically within our smart contract. And then finally, we have this method for deleting our application. Now, this is an important thing to note because being the ledger itself is immutable, but that doesn't mean we can't remove things from it. So in the context of deleting an application, what we're basically doing is we're removing the requirement for every node in the network to hold this application and hold this logic. However, every node in the network, if they were to replay the history, they would still see this application previously existed. So just because we're immutable doesn't mean that we can't have some flexibility in how the state changes. It just means that any change to the state can always be referenced in the future. And so, again, we're just asserting that that this is being called by the correct person, and then we're issuing some transactions to send the remaining assets to the seller, right? So let's say, I have a listing, 50 people have bought my tokens, but I, still have a couple left over. I want to delete the application and get back all the unsold tokens. And so that's what we're doing here by transferring those tokens with an asset transfer and submitting it to the network. And then we do the same thing with a payment where we send all the money that people have sent us to buy our assets to the seller. So when I no longer want to sell my asset, I delete the application. And because I've reduced the size of the ledger, I get some of my money back. And then I get all the money that was sold and any leftover assets. And once I have fully generated or fully wrote my contract, I can now see I can also test my contract. So if we come to project tests, and we come to our digital marketplace test, we can see here that I have a test suite written in with Pytest, and I'm using that AlgoKit utils library in order to interact with a local instance of the chain. So remember, the command line tool is called AlgoKit, and this is just a tool that you can install. You can just do pipx install AlgoKit, and then you can do a local net start. And what that's going to do, I had to restart my computer because I had it hang as I was doing technical testing. So let me restart Docker. But while that's restarting, what AlgoKit allows us to do is start a local network in the background, right? So in order to transact on the network, you always need to pay a fee. But as we're testing our contract, we of course don't want to pay millions of dollars just to test it and not actually have any users use it. So instead, we have basically a local blockchain running on a local computer, in this case through Docker. Let me see if Docker has started yet. And we can see that we can start a local network. And what this allows us to do, if we kind of go in and we take a look, we can see that we can send transactions to the network, we can interact with our app on the network, and then we can assert state about the transactions we send. So we can see here that we are calling a method, and then we are asserting that transaction has been confirmed, and then we're asserting balances in the network. And so we're using that AlgoKit utils library to interact with the chain. Now it's also really nice, and we can see that if I do an AlgoKit project run test, we can see here that it's going to run poetry run test, which executes all these tests, and it ran successfully. But because we're using AlgoKit, it also ran all the tests in my front end as well. And so AlgoKit provides those utilities for interacting with the chain and being able to run those tests. But what's also really important in AlgoKit is that it's able to provide what we call a generated client. So I'll come back to our contract. Every single method we defined uses this arc4 ABI method, right? This is a standardized way to define how we interact with contracts. And because we use a standardized way to interact with contracts, we can auto-generate the code that leverages those standards. So if we take a look here at our imports, one of the things we import is from this digital marketplace client. So if we go and take a look at that, we can see here we have hundreds of lines of code that was automatically generated for us just based on this contract.py. And what this allows us to do is if we take a look at our tests, we can see in order to call, for example, the buy method and buy an asset, I simply call my digital marketplace client dot buy, and I call it like any other method on any other Python class. And I pass in all of my arguments. And the key is that this removes basically a necessary step of connecting my, in this case, my Pytest code. It could be your backend code, your front-end code, from connecting that to your application. With AlgoKit, we automatically generate that client, and it is able to provide a very simple interface, in this example, a buy method, for calling the methods we define in our contract. So by using Python, we're able to write all this logic that is actually executed on chain. And we can verify, for example, in this test buy, that I can actually execute a transaction, send some algo, which is the native token on our blockchain, to a contract and get back some asset. And most of that logic was executed in this buy function call, which was auto-generated by AlgoKit. So really the key here is that by adopting Python, you can just focus on writing the logic, and we'll take care of everything else for you. So you don't have to worry about how you do the ones and zeros to interact with your contract. You don't have to worry about how you connect your test or your backend to your contract. We do that all for you, and what you have to care about is your business logic and how you actually implement it as infrastructure in your project. Now, I know this was a pretty quick run through of what Algorand on Python looks like, and there's definitely a lot more to learn. So if you are interested in learning more, you can, we have 2 QR codes. The Get Started with AlgoKit QR code is if you are interested in how to install AlgoKit. It's pretty simple. It's just a pipx install AlgoKit. And that will allow you to get that CLI tool and start creating, trading projects, developing contracts, testing contracts, and deploying products. And if you want a more in-depth look at the contract that we built, so that was a digital marketplace contract, and you want to learn more about kind of the details and the technical capabilities of Algorand, you can attend our boot camps. And so in the past, we did a beginner boot camp that went over that contract that we just did, and we have recordings available for that. Or you can sign up for our intermediate boot camp, which is going to be building on top of the concepts that we've implemented in that digital marketplace contract and learning more concepts about Algorand. And again, that QR code is where you can get the resources for both of those. So I know we're coming close to the end of the time here, but I think I can stick around for a couple more minutes if there are any questions. So are there any questions about Algorand, Python, blockchain in general? I'm happy to answer them. Any questions? Okay, if not, then I encourage you all check out the Get Started page with AlgoKit and join our boot camps. If you join the boot camps, you'll see me there. I'm running the boot camps, and happy if you see me around the conference, happy to answer any questions. Thanks, everyone.